Okay. Yeah, you got the notes? You got the notes? Got the notes, yeah? There we go. Okay, sorry for the little bit of a technical problems. Gonna start now. So last week, I think there are some classes who did this, some classes who didn't. Last week I went on to talk about this thing here. Uh, mentioned that this is a this is a ring, right? But specifically, this ring cannot be made of um iron or steel. Okay, right? This ring cannot be made of iron, cannot be made of steel, right? Basically anything magnetic. So whenever we deal with this kind of like questions in EMI, in EMI, right? We basically have to use non-magnetic conductors because if they're magnetic, right, they'll just swing and get stuck over. Then you won't see the electromagnetic induction effect. Okay. I showed a little bit of a YouTube video, something that's similar. Actually, there is one other video that I've sent before. Hang on, let me. Oh man, I'm in a mess this morning because I've got so many things going on. Hang on. So this is a ring and magnet, something like that. Ah, there we go. Okay, hang on. So I'm gonna send this is Instagram. I don't know whether you guys still use Instagram. But if you don't, I can just record my screen as I see it. But yeah, it's a mm, yeah. So anyway, so that's a video I just sent out, which is something related to this. Essentially, you know that this ring, as it swings towards the magnet, okay. Just a bit of warm up. What happens first? What do we talk about first? As the ring swings towards the magnet, there's a change in flux. Good, right? That's exactly the four steps that we start off with. Change in flux. What's the next one? You have the notes, right? Wait, if you don't mind, just go outside and get it. It's just outside. It's gonna be done soon. Sorry. Good Monday morning. Number two, what was the second step? You said change in flux, and then what? Induce EMF. Good. All right. So you're basically just following the four steps that I mentioned last week. All right. It's gonna be the standard four steps. And then number three, what's the number three? There'll be induced current. And then number four, there'll be by Lenz's law, there'll be opposing force. So for number two and number four, if you can, right, quote the law. So Faraday's law and Lenz's law. Okay. Then there'll be opposing force. Is that right out there? Right. So Faraday's law, induced law. Faraday's law tells us that the induced EMF. Lenz's law tells us there's opposing force. Same four standard steps, right? So get it in your head. So it's like means so that we don't have to spend that much time trying to go through these four steps over and over again, trying to get it in the head. If you have to, please do that at home, right? Just try to memorize these four steps because we're gonna have to go through. We're gonna spend the more most of the time to go through different scenarios because the different scenarios are the ones that's a bit more mind-boggling, right? If you want the whole, the whole detailed lesson, right? Yeah, that's what you got to do. Okay, so as the ring swings towards the, the magnet, the ring is going to experience an opposing force. So there'll be an opposing force, which then cause the ring to swing slower. Okay. Yeah. So I did send out the video, as in I just did, I sent out the Instagram. I don't know whether it's like, you can see it. Like, why not you just look at it? Yeah, it's an Instagram video. Yeah. So I'm asking you to look at Instagram now. So look at the difference between, right, the two things. Ben, are you looking at the link? Then it's fine. Right. So like, you all can see the difference, right? So there's one. So for this video, they're pushing the magnet towards the ring, right? For this example I have here, the ring is swinging towards the magnet. The effects will be the same. So notice what happens when he tries to push the magnet into the split ring, right? And then what happens when he tries to push the magnet into the whole complete ring, right? So if you don't have Instagram, just look at his phone. It's fine, right? It's just the demo. Isaac, is look at his phone. Yeah, as in, oh, have you seen it yet? You've seen it already? No, I'm literally asking you all to look at it, right? So if you don't have Instagram, that's fine. Just look at your friend's phone, right? So if you look at it, right, so you have your split ring, okay, and then your complete ring. Okay, anyone tell me why? What's the difference? Like, these guys are trying to create content, right? So they ask a question like, explain why using lenses law, right? So the question is whether you all understand the answer or not. So what's the reason? Do you see it? Okay. And then good. There you go. All right, excellent answer. Yeah, there will be, right? So there will be. So if you use the split ring, right? If you use a ring that has a gap, okay, and you let it swing towards the magnet. So the difference between my example here and the one in the video is that I'm swinging this ring, right? The video is pushing the magnet in, same thing, okay? So I'm letting this thing swing towards. So what happens is that there will be Faraday's law, there will be induced EMF. That's the thing, right? Because there's still a change in flux. What is flux? Flux is basically magnetic field lines that's cutting through the area of the coil. So your area of the coil is here like this. Yeah, it's still a coil, right? So it's still a coil, right? It's area, even though the area is not complete. So I mean, it's like almost complete. So there's like some sort of like enclosed area, almost enclosed area. There is still a change in flux. Yes, there's a change in flux. There's still induced EMF. If you connect the ring to a voltmeter, you will see the voltmeter jump, right? The voltmeter will give you a reading. So there will be still induced EMF, right? But the thing is that it's an open circuit, right? So like what she said, okay, there's no induced current. There's no induced current. There's no opposing force. Okay, but there is still change in EMF. So this is the part where some students get a bit confused. It'll be like, I thought voltage and current is the same thing. So that's what happens when you try to oversimplify things in your head, right? You tend to think that, oh, voltage and the current and current is the same thing, right? So why is there a difference, right? So when there's voltage, there's current, right? So when you do that, you basically oversimplify and you lose marks, right? And you have no idea why, especially for those who are taking the O levels, because you kind of like just wanted to simplify it into your head, right? Like I say again, appreciate the complexity, right? There's voltage, but there is no current, right? Because the circuit is open. And then last week I did go through this example, so I'm done with that, right? So there's the explanation. There's no opposing force. So if this ring is swinging towards the magnet, it will just swing freely. But if this ring is swinging towards this magnet, then this ring will like kind of like slow down. It won't swing as fast. It will like, like that. Yeah. And this guy would just like probably swing past and probably hit the magnet as well, right? And again, it's not a magnetic material, so it won't be attracted by the magnet. Okay. And last week we went through this concept here, right? Where there's battery and then there's a switch, right? And then I think just a recap. So we mentioned that when you close the switch, the light bulb will light up, right? When we close the switch, the light bulb will light up. Like why? Again, one more time. What's the whole explanation? But this time around, added explanation, because you have to talk about this thing here. There's no magnets now, right? There's no actual permanent magnet now, so you have to describe the whole thing, right? Me, you go and look at the exam paper, okay? So this is not me what giving you a more challenging thing or anything like that, right? So like, yeah. So what happens when you close the switch? What happens to the left coil or coil A, right? Call it coil A, right? When you close the switch, what happens? Yeah, it becomes an electromagnet, right? So there will be a current flowing through it. It becomes an electromagnet. So this electromagnet will have a pole, right? It will have a pole, right? Did we talk about what pole it was last week? Did we talk about the pole? Did we label the pole? I don't think we labeled the pole, right? Yeah, I don't think we labeled the pole. So, according to this picture, right? According to this picture, what pole is on the right side of this electromagnet? South pole, good, right? So this is south pole. Okay, it's a south pole. Okay, how do you know? Tell me. Right hand grip rule. So this one's quite obvious. Right hand grip rule. Put your fingers up like this, right? So it's going up and around, up and around. So that's the south pole. Okay. So then describe to me what happens to this coil. You see, this coil is connected to a bulb. It's not connected to a battery. So this coil is going to experience something. So what's the 1, 2, 3, 4 thing? There'll be change in flux. There'll be induced EMF. There'll be induced current. Now, you don't need to quote 4 here. Will there be an opposing force? I mean, yes, there will be, right? There will be opposing force, right? But that's not the main concern of this question, because the question is asking you, why does the bulb light up? The opposing force does not have anything to do with the bulb lighting up. Also one more thing. In previous batches, I've had students who done this before. Opposing force, EMF, electromotive force, then they put one and one together, then think it's the same thing. Oh, EMF is the same thing as opposing force, right? Then gone case, everything is like like up in smoke. Right? So if you hadn't realized it's not one and one the same, it's not the same thing, okay? Right? So once you get EMF, you get current, okay? Yes, you see, right? I mean, you look at the coil, what will the coil try to do? Like at this instant, once you close the switch, what will the coil try to do? The coil will try to oppose the change, right? So there's a sudden increase of a south pole. Let's say, for example, there was no south pole at first, and then suddenly there's a south pole. So what would this coil try to do? By creating what? Yeah, by inducing a south pole on this side, right? It will induce a south pole on this side. Use your right hand grip rule. Use your right hand grip rule. How does the induced current flow in that coil? Yeah, good, right? Right grip rule. So you all understand that the chopping part of your hand has to be at the south side, right? Like this. Okay, so it goes that way. Okay, right. So then you trace current like this, and then yeah, the idea is this. So is there a repulsion force? Is there an opposing force? Yes, there is between the two of them. In fact, these two coils, right? I mean, if you think about this, if you look at the video there, you realize that these once you close the switch, right, these two coils will actually shift away from each other. They will literally repel from each other. Correct? But that doesn't help you explain why the bulb lights up. Our focus of the question is asking you, why does the bulb light up? So if you were to say something like, oh, the two coils will repel each other, what's the teacher gonna think? The marker's gonna be like, you're right, but that's not the focus of this question, right? And if you end off there saying that the two coils will oppose each other without explaining why the bulb lights up, you just lose the mark, right? You get what I'm saying? Right. So when you apply 1, 2, 3, 4, apply logically as well. Don't just apply like I must talk about the opposing force because Sam says must talk about the opposing force, right? It's like you gotta read the thing. Okay. Yeah. Then we did mention that what happens if after I close the switch and describe what happens after a while. Like after a while, like like once the switch has been closed for maybe like a good 5 to 10 seconds later, right? What happens then? Like, so what? Yeah, so the bulb will go off, right? Then another 2 mark question, right? Part A, part B, part C, right? Part C, they ask you 2 mark question. Describe what happens after the switch has been closed for a while. right? Then what do you say? The bulb doesn't light up, but why? And then why is there no change? No. I mean, it doesn't light up because there's no induced current, there's no induced EMF because there's no change in flux. But why is there no change in flux? Because the current is steady. So the words I used last week, right? I said that the current is steady, the flux is steady. So 5 to 10 seconds later, current in A is steady, flux magnetic field of A is steady. So B doesn't experience a change in flux. Then the bulb will go off, right? So just a while later, after the switch has been closed, right? Just a while later. So once you close the switch already, right? 5 to 10 seconds later, I mean, it's not specifically 5 or 10 seconds. They're just giving you an amount of time, right? Because if I were to say something like, oh, a little while later, you might be thinking a little while later is what? That's like at the end of the day, or what? 3 hours later? What's a little while later, right? So 5 to 10 seconds later, right? Current in A becomes steady, right? Magnetic field becomes steady, right? And then basically says no change in flux in B. No change in flux in B. Sorry, just trying to wrap up this recap from last week, right? Because we did this last week as well. We got now these are the easy cases. When you get north and south, it's easy to understand. Right? When you get the north and south, when you can see where the north is, when you can see where the south is, it's easy. It becomes easy. This is like level 1. You need to get to level 2. Level 1 is when you see like, oh, I can figure out where the south is, right? I know that this coil will do an induced south, right? To oppose the change, and therefore you 1, 2, 3, 4, 1, 2, 3. So then the bulb lights up. What's a little bit more difficult is when you can't see north and south, which is on the next page. Okay? On the next page, right, we have a scenario here, right? Do me a favor, I kind of like I realize that the triangle is a little bit like over the top. So use some blanco, right? Use some blanco, legit use some blanco, and then just change it to a rectangular loop. Okay, change it to a rectangular loop. Okay, yeah. Use a white pen if you're using a pen. Right. Change it to a rectangular loop. Rectangular. Okay, so I'm gonna change it to a rectangular loop like this. Let me just make it a bit thicker. You know what? Let me use another color. So this is a rectangular loop of wire. Okay, right? I don't know how else to describe this to you other than to kind of like tell you to imagine this coil is in a rectangular shape, like kind of like you shape it into a rectangle. That's it. That's what you're looking at. Okay, this is not a metal sheet, so it's a rectangular coil or rectangular loop. So maybe it will help you to write down rectangular loop of wire, because if you're doing revision, suddenly you look at this thing, if you didn't write this down, right, then you'll probably be thinking like, oh, that's a piece of metal. It's not a piece of metal, it's a rectangular loop of wire. Okay, so it's not that hard to understand what it is, right? Okay, so it is this thing here. So what we want to do is we want to pull this loop of wire into this field, right? Pull it all the way to the other side. You know what I'm saying? Okay. Now this is a like slightly silly question, right? But hope you don't get it wrong. As I'm pulling it in this empty space here, now there's a magnetic field. Look at all the crosses. This is the magnetic field. But as I pull it in this empty space here, right? Is there any induced anything here? Is there a change in flux, or is there any induced? Is there any Faraday's law or Lenz's law happening in this region here? Don't have, right? Okay. So I'm gonna tell you that once you pull it in, once you start pulling it in, it will start experiencing that 1, 2, 3, 4. Okay. So it will start experiencing it like this. So imagine this loop of wire now being transited over to here. Like it's kind of like partially in, partially out, of the field. Okay, partially in, partially out of the field. right? And basically something is gonna happen here. Why? So so imagine this rectangular loop of coil. What is it experiencing? It's experiencing a change in flux, right? A change in flux is a change in flux. So here's the thing, right? This is the magnetic field, right? It's just that you're looking at the magnetic field going into the page. Now, if some of you like, no, I can't visualize this. I can't visualize this. Let me help you, right? Let me draw it out for you. Let me show you what you're looking at. Okay, you're basically looking directly at the south pole, but like I said again, the second level of understanding is not to use poles to understand, right? So don't try to revert back to that style. Okay, I'm just trying to show you that if you had a south pole magnet here like this, you have a south pole magnet here with a north pole on this side here like that. Okay, let's say this is a north pole, and the magnetic field was going this way. You all understand, right? Magnetic fields will go this way, right? Okay, magnetic fields will go that way. Like, how does the magnetic field, like, go towards the south pole? It enters the south pole, right? So if it enters the surface, is on them crosses. Cross means going into the page, right? We've done this since, like, I don't know, magnetism already. So crosses means going into the page. So what you're looking at is you're looking at the surface of a south pole, right? Okay, right? That's all, right? If in case you look at all these crosses and like, oh, I don't understand why these crosses are magnetic field lines, right? They are. You're just looking at it, not from the side though. You're looking at it face on like this, and it's going into the page. Okay. But yeah, back to the coil, right? And I said, let's not deal with north and south. Let's learn how to do EMI without the north and south. North and south is level one. This is level two. Is the loop experiencing a change in flux? There's a change in flux, right? So 1, 2, 3, 4, right? There'll be a change in flux. So 1, there's a change in flux. Okay, right? I mean, who's experiencing the change? Is the magnetic field changing? Is the magnetic field changing? The field itself is not changing, right? Yeah, it's not changing. What's changing? The flux. What is flux? Flux is the field lines cutting the area. I went through that last week. That's the first thing. That was the first thing I went through last week, right? So this loop experiences a change in flux. So will there be induced EMF? There will be. Will there be induced current? Check. Is it a closed circuit? It is, right? I mean, it's a rectangular loop, right? So yeah, there's a closed circuit. So there'll be an opposing force and all that. Yeah, that's fine. Okay, so now the big question is this, right? So we go with 1, 2, and 3 first. Let's talk about, right? Let's talk about induced EMF, and then let's talk about induced current, right? Because it's closed circuit. Let's talk about induced current. Let's talk about the direction of the induced current, but no north or south pole. No north or south pole. Okay, right? Now, yeah, I know some of you in school, you already started learning right hand rule, but I'm trying not to use the right hand rule here. You can, I'll show you how to later on, but I'm teaching you another method of finding the induced current without, yeah, without the right hand rule. Okay. Now, hang on. Has your school started on EMI already? Started on EMI? No, not yet. Oh, okay. Teachers different pace. Okay. Huh? Tried to start a bit. Okay. Oh, then why he teach right hand rule? He's not supposed to do that yet. Yeah, if he starts off with this, it's gonna be confusing. Yeah, it's gonna be hella confusing. Haven't started yet? Oh, you are very far away. Okay, finally picking up the pace. Where are you? Magnetism. Why is it so different, the pace? Yeah, but no, but magnetism, then there's electromagnetism, then there's electromagnetic induction. You saying a teacher is, just started electromagnetic induction. What the? That's damn fast. Then yours is what? Just started on magnetism. Yours? Did you just say radioactivity? What? That's even fast, man. That means you finished AC generator already. Whoa, okay, that's scary. Wow, everyone's pace is all different all over the place. Oh, that's a bit scary. Okay, anyway, right. Hey, Kobe, what did you tell me just now? Oh, okay. What was it again? Finishing DC motor? Haven't reached it yet. Okay, halfway. Wow, everyone's all over the place. Okay, doesn't matter. Right. So what happens here is that this coil is now entering, right, a magnetic field, right? So it's experiencing a change. Let me ask you, imagine you're the coil. What is the change that you're experiencing? Not what that not asking you to describe what you're experiencing, but I'm asking you what change are you experiencing. So what is that? I mean, that's what you're experiencing, but what's the change then? Right? Specifically, what's the change? So when I ask you for the change, right, it's basically either the increase or decrease, right? So does it experience more? It's experiencing more flux, right? So the flux is increasing, right? So specifically, the change is increasing, but the flux is pointing where? Where's the flux pointing? Into the page, right? So basically, this coil is experiencing more crosses, right? I'm just gonna say it's experiencing increasing number of, like, magnetic field lines going into the page. You understand what I'm saying? So the change in flux is that it's experiencing, right, an increase in the number of crosses that's going into the page. Okay, so will there be induced EMF? Yes. Will there be induced current? Yes. What's the direction of current to oppose this change? So don't forget the current. Lenz's law tells us that, okay, if you have induced current, it will try to oppose the original change. The direction of the induced current will oppose original change. So if you're experiencing more crosses, how do you try to oppose it? You're saying that you want this loop to create field lines pointing out of the page. Yeah, that's absolutely right. So what happens is that this loop, right, will try to create its own magnetic field, and its own magnetic field is pointing out of the page like this, right? In magnetism, if you remember, I think I mentioned this before. If you have one magnetic field pointing this way and another magnetic field pointing the other way, even if it's from a different source, if you have one magnetic field pointing this way, another one pointing that way, they will cancel each other out. So that's what this induced current is trying to do. It's trying to cancel the increase. But in doing so, it will induce its own induced current and induce magnetic field. So you use your right hand grip rule, right hand grip rule, right? Show that the thumb is pointing out of the page, right? Because you're trying to induce this magnetic field, and therefore the current will flow anti-clockwise, right? So even though it's a rectangular loop, you can also use your right. You can also use your right hand grip rule, right? Because it gives you the general direction of the current. You understand this? So this is when the loop is like going half in, half out of the field, right? Kind of like on the way in. Now the thing is this: what happens when it's fully in the field? Like, what happens once it's fully in and you're still pulling it like this, right? This is a uniform field. That means the crosses are evenly distributed. The area of the loop doesn't change, and you're still pulling it with a constant speed. So what happens when the loop enters fully into the field? No more change in flux, right? So there's no change in flux. Why? Because the magnetic field is uniform, right? The area is constant. So there's no change in flux. And if there's no change in flux, there's no induced EMF and there's no induced current. And there's no opposing force either. Which means that in this example, when you pull this loop in, you're going to experience a opposing force here, no opposing force here, and guess what? Once it comes out, what happens when it's on its way out? Yeah, you'll experience it again. But this time around, I want you to use the same idea and try to work out the direction of the induced current, right? So the whole process is a very simple process. I'm just pulling a loop of wire across a magnetic field. That's it. Like, pull, right? It's not some like, oh, I'm trying to build a rocket science, slap on an engine, make it ignite, like fly it to space. No, I'm just pulling a coil across the magnetic field. Okay? But here's where it gets interesting, right? This is where it might, like, I don't know, some people get it, some people don't, right? So if you don't get it, don't worry. right? Just run it through your head a couple of times, right? You get it eventually, right? Like the national anthem. So looking at this loop here, it's on its way out, right? Because someone is pulling it. Like it's always been going up, like someone has always been pulling it, like someone has always been pulling it all the way there, right? Like this. Can you describe what's the change here? There's a change, but what's the change? There's a decrease in the number of crosses. There's a decrease in the number of crosses, right? So as you're pulling it out, there's a decrease. It's getting less. So what will the loop try to do? It will try to create more of its own, right? Like flux that's pointing into the page. So this is like the blue crosses is the flux that the coil induces by itself, right? This is the coil's own magnetic field lines, right? Because it's experiencing like, oh, why is the field disappearing? Let me try to create some of my own. Notice how I emphasize that it's always opposed, right? It's not opposite direction, nor is it like repel or anything like that. Okay, so it's always opposing the change. So yeah, so very a lot of people get understand this because they see the cross, they see the dot, then they think that, oh, opposite ma. But what a lot of people don't understand is what happens when the loop comes out, and then how come same direction? I don't get it. Why is it same direction? Because you keep thinking about it as the opposite direction. It's not opposite direction. It's opposed the change. So you gotta tell yourself what's the change. The change is there's an increase in flux. The coil will try to reduce it. There's a decrease in flux. The coil will try to increase it. Okay, so it's not about trying to oppose the direction, yeah, or repel. Okay, so using your right hand grip rule, what's the direction of current in the coil over there? Yeah, clockwise. I know it's going to be opposite, lah, right? But you use your right hand grip rule, you know that it's going to point into the page and therefore it's clockwise. There we go. And this should settle, or rather, this kind of like this whole complex thing, right? If it comes out in the exam, right, this can easily settle like a 6 mark to 8 mark question, like if they ask you in many parts, right? 6 to 8 marks, right? So explain why, explain why, explain why, explain why, explain why. Okay, now here's the thing: will there be an opposing force? Will there be an opposing force? Well, I talked about induced current, but I haven't talked about number 4 yet. I haven't talked about opposing force. Will there be an opposing force? Yes, there will be. Right? Do you want to talk about opposing force? Do we want to talk about an opposing force? Probably, because there's no bulk here. Right? We're not trying to light something up. Right? We're trying to pull a coil across. I think that's pretty much it. See the induced current. Then maybe they want to follow up with a opposing force. So let's talk about opposing force then. Okay, so number 4, right? There's a opposing force, right? But when does the opposing force act? Like at which times? Only on the entry and on the exit. It doesn't happen in the middle. So you get opposing force here, right? You get opposing force here, and you get an opposing force here. Okay, right? Opposing force and opposing force here. Is this opposing force a form of repulsion? Is it a form of attraction? The answer is no. Right? Neither. Right? It is not a type of attraction nor repulsion. It's just kind of like a force that acts against the movement of the coil. Right? But it's not specifically repulsion or attraction anymore because we are not going towards the pole. We are going perpendicularly to the pole. It is a magnetic force. It is a type of magnetic force, but it's not a repulsion or attraction specifically. Okay, but it's still, yeah. Do you, yeah? But if you use this, then you have to use it on the side that's in the field, not on this side, because this side is not in the field yet. But the reason why this side has an induced current is because this side creates a current and the current flows inwards this way. But I haven't gone there yet, so I'll come back to this later. Yeah, I'm not done. I'm not fully done with this yet, guys. Yeah, I'm not fully done with this yet. Right, I'll come back to this later. What I want to do is I want you all to draw the graph for this, right? For this loop going into the magnetic field. So we're going to draw the voltage time graph. So what happens as you pull this loop along, right? How will the graph look like? Now it's not an overly complicated graph. I'm just gonna draw it, right? And we just try to investigate why it looks like that, right? So I'll draw it down here now. I'm trying to kind of like match it to the point whereby it enters. Not exactly accurate, doesn't really matter. Hang on, let me draw finish first. Then you can start drawing. Right? Yeah, but the graph will sort of like look like this. Like if this was the sequence of the loop going into the field, then the induced current will be like here, like this. It will be a rectangular shape because the loop is a rectangular shape, right? You don't have to worry about triangle shape. I don't think any of your schools is at the kind of level where they can ask you a triangle shape. If you do see it in your school homework, please let me know, right? Of course, I'll go through that with you, right? But for rectangular shape, right, then the thing will be like this. So there'll be induced EMF. We talked about this. There'll be induced EMF that we understand why. The induced EMF will be a constant value, right? Look at that. The induced EMF, it rises from zero. It starts from zero and it goes up to a constant value here like this, right? Or rather, you can think of it like it goes from zero and goes up like this, constant value, right? Simply because the rectangular loop is a constant, right? Constant like area and is moving constantly. But once it enters the field, it's zero. Once it's coming out of the field, it has induced EMF again, but this time around it's in the opposite direction. Look at that. The current here was anti-clockwise, and the current here is clockwise. So the induced EMF will whoop the other way around, like that. You know what I'm saying? Right? I mean, they could simply ask you, explain why is it positive and why is this negative, right? Then you have to say that as the loop was going in, it's experiencing a increase in flux, right? But as it's leaving, it's experiencing a decrease in flux. So the induced EMF is opposite directions. What most students mistake, right, is that they say this now, oh, why is it opposite, right? They say, oh, it's due to Lenz's law, right? It's due to Lenz's law. No, that's not true. Lenz's law tells us that there's an opposing, like the current is in the direction to oppose the change. The current that's opposing, like Lenz's law exists at both areas. The key difference between entering and leaving is because there was an increase in flux, so the coil tries to oppose that, and then there's a decrease in flux, so the coil tries to oppose that. Therefore, it becomes positive and negative. You should not quote Lenz's law. Like any teacher who is just a little bit more stringent in marking would I mean, if they are marking this, if I'm the marker, I would know that the student does not know what's going on and then just simply say that, oh, opposite means Lenz's law. That's not acceptable, right? Because Lenz's law applies at both sides. How do you explain then why it's positive and negative? It's strictly because increase in flux, decrease in flux. Okay, Liz? Can I? Right. So we'll come back to this, right? We'll come back to this because some of you already started doing this right hand rule in school, right? I haven't shown you yet. I kind of introduced it to you last week. There's three hand rules in total: right hand grip rule, left hand rule, and then there's a right hand rule. But I have not done right hand rule for good reason. I don't want to do that yet because I want you to learn this kind of like telling how the direction of the induced current is. Okay. Then yet an even harder one will be this one here. This one will be a little bit more advanced than this one. Okay, but we're just leveling up, right? Otherwise, you want me to do it the other way for this one, repeat this question, but then move the coil backwards. All right, ain't nobody got time for that. Okay, so we have one big coil and one small coil. So what's that? So one of the ways of imagining it will be something like this, right? There will be an inner coil, and then there's another one outside lah, bigger one lah. That's it. Okay, so there's one big coil and one small coil. Or they may give you a very complicated drawing. Let me show it to you. Let me draw it out for you. Okay, so I am already trying to simplify it for you, right? But sometimes the drawings is really very complicated. Let me show you this. Okay, sometimes you have one coil like that. Okay, right? There's a coil and there's current flowing in. Okay, and then I wrap a small coil in the middle, kind of like I just have a small coil in the middle like this. You get what I'm saying? Yeah, this is like having a big spring and a small spring just intermesh each other like that. That's pretty much it, right? Don't forget the coils are all hollow. Okay, so you can like kind of like, yeah. Then yet when you kind of like, if let's say you have this in 3D or something like that, right? And then you kind of like look at it face on like that. When you look at it face on, what do you see? You will see one big loop on the outside and then one small loop on the inside like that. Right? and then the current of the big loop will be like flowing in a certain direction. Okay, I'm gonna ask you this, okay, right? Let's say there's a current flowing in the outer loop, and then the inner loop is connected to a voltmeter. Let's draw for you a voltmeter here like that, a voltmeter like this. Okay, I'm gonna ask you this, So this inner loop has a voltage. I mean, has a voltmeter connected to it. You just can't really see it from this direction, right? But I'm gonna ask you this. Let's say the current on the outer loop is constant. It's a constant current, constant current, constant current on the outer loop. Is there induced EMF in the inner loop? Is there induced EMF? No, right? In fact, right, for the outer loop, does the outer loop have a magnetic field? Does the outer loop have a magnetic field? Does the big loop have a magnetic field? It has, right? Why does it have a magnetic field? It's a loop with a current, electromagnetism, right? Okay, the current is flowing this way, right? So there's magnetic field from the big loop pointing into the page like this, right? So there you go, right? There's a magnetic field. So I'm going to use the black color to show you that this is the magnetic field of the outer loop. So I'm gonna ask you this: does the small coil experience flux? Is there flux? Hang on, listen to my question. Does the small coil experience flux? Is it experiencing flux right now? What is flux? Flux is when the magnetic field is cutting, magnetic field is passing through the area, right? So it's experiencing flux because there's magnetic field passing through the area, but does it experience a change in flux? So you see, right, this is the small little thing that a lot of teachers like to test on. So there is flux, but there's no change. So is there induced EMF in the smaller coil? Don't have, right? So no induced EMF. Okay. So maybe you want to make a small little note, right? Smaller coil experiences flux, but no change in flux. So no induced EMF and no induced current. Okay, right now, if the outer coil current is constant, so at this point, I've had some students from the past before. They basically just tell me that basically everything is the same thing, right? It's always about this. It's just like the same thing over and over and over and over again. It's like step 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, it is. It is. It wouldn't be. I mean, yeah. So EMI is actually one of my least revised topics. Because once you understand this, right? Once you understand it like this, with all the kind of like the stages I've gone through with you, level 1, level 2. Once you understand this, like that, no point revising this chapter one. I rather spend a lot more time revising other chapters, man. Okay? Because there's no equations, there's no calculations. It's just you trying to figure out the perspective of it. Okay? Anyway, so there we go. Something's gonna happen. So in this question here, it didn't say. In this question here, so this is the tough part. The current in the outer loop is decreasing. Okay, current in the outer loop is decreasing. Right? So current in the outer loop is decreasing. So let me draw the crosses again. Right? Okay, one more time. These crosses belong to who? These crosses belong to who again? One more time. The bigger loop, right? The outer loop. So I'm just drawing a few. I'm drawing a few. Okay. So the current is decreasing. The current is decreasing. Okay. All right. What happens to these crosses? They start to. So current decrease. So what happens to the magnetic field here? What did you say just now? It'll be lesser, right? So they start disappearing. Now it's very hard to animate or draw that in your papers. I understand that. So maybe you have to put a note on the side. Okay, right? Because here's the thing, they won't ask you to do this in exam, but I'm just trying to show you, right, visually, this is what happens. So even if you don't take this down, but maybe you can videographically remember what I'm saying here, that'll be great, right? But basically the crosses will start to disappear. They'll start to getting less and less and less. You know what I'm saying? So the inner coil, let me draw a blue color for the inner coil because just to follow the same color coordination that we had just now. Okay, what's gonna happen to the inner coil? Like what would the inner coil try to do? The smaller one. He's trying to create more crosses, right? Yeah, right. He's trying to induce more of because the crosses are disappearing. He's like, hey, no, don't go away, right? So he will try to create more of his own, and in doing so, the induced current will be clockwise in the inner coil. So the inner coil will have its own induced current clockwise. As long as the outer coil, right, the current is decreasing, the inner coil's induced current is clockwise. Right, so I'll just put a CW there, clockwise. Like this. Yeah, sort of makes sense. Okay, so that's really one of the highest level ones actually, right? Because there's no north or south pole, right? And nothing's moving. There's no movement. This is moving. You know, this is you understanding the true idea of what Faraday's law says. There's a change in flux, and the induced current will try to oppose it. You can go and play around with it. You can try. Oh, what happens if the current starts to increase? I mean, there's only two ways about it, right? The outer coil, either the current, I mean, three ways. The current either decreasing, steady, or increasing. Okay, that's only three scenarios only. So if it's decreasing, the induced current is going this way. If it's increasing, then the induced current will go the other way lah, right? Because it's trying to fight against the increase in field, right? So you try to create a field that's pointing out of the page. You know what I'm saying? Yeah. So these are the scenarios. Okay. Um, we'll go through one more thing here before we take a quick break, right? Because these are all very mind-boggling. Okay, we'll try to take a quick break. So the idea here is we have a wire, and then there's a loop, right? There's a loop around next to the wire. Okay, this loop again, this loop here is essentially this loop of wire. Okay, right? This loop of wire here like this. This is the loop, right? What I want you to note, I want to ask you is this: does the loop experience flux? Think first. Does the loop experience flux? Suddenly, there's no more magnets. It's like you see, I've completely removed all the magnets already. Right? You're on level 2.5 now. You're on level 2.5 now. There's a wire. It has a current, and then I place a loop next to it. Then I ask you the question is, does the loop experience flux? The answer is yes. There's flux. Okay, where's the flux coming from? It's coming from the wire. So you see, right? The idea here is don't forget about electromagnetism. You have a current, right? It has a magnetic field. So how does the magnetic field of a single wire look like again? You all do the right hand grip rule, right? So your understand is a circle, right? So if you look at all your school's textbooks and all the notes and all that, you will see the thing going like this, right? Do you remember in electromagnetism I say I don't like to draw it like this, right? I say I don't like to draw it like this, like huh? What? Sorry, what? No, this is the steady current, steady current. It's a steady current. So there's flux, but there's no change inside this. Yeah. Okay. So, but I want to draw how the magnetic field looks like from the wire. So the magnetic field looks like this, right? I love to draw it like that, right? I do not like to draw the circles because the circles is not quite right. Okay, but it kind of like looks like this, like that, right? So cross going in and dot coming out, right? So this is the magnetic field of the wire, this one here. So right now you can see magnetic field cutting into the loops area, right? So there is flux, but there is no change. So if there is no change, then there's no induced current. Okay? So got flux, but no change. Right? So has flux, but no del flux. Right? No change in flux. You all learned this, right? In math, del is change, right? Right? That was differentiation, isn't it? Wait, you don't huh? No, 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 hang on. In math, you don't use this del, you use a small letter del. You use this. No, do you? You don't even use this? You just go straight into dy dx. Ah, I see. Okay, and that's fine. I mean, yeah, del means change. I'm just saying that in math, I'm just trying to figure out whether they show you the triangle in math or they show you this like cursive D in math. You don't? Okay. I'm just trying to figure like what kind of math you're getting. Anyway, okay. Now the thing is this, right? So this thing, right, is meant to for you to understand something else, right? The idea here is that there are sometimes some wires embedded in the household walls, right? Like my wires are not embedded. Like, I mean, look at this, right? The wires are all inside the plastic conduits, right? There's one over back there, right? This. I mean, you look at the plastic, you know there's wire inside, right? I mean, there's no need to go and like think about whether there's a wire inside, there's wire inside. But how about your homes? So some of your homes have been renovated, right? Your parents like to conceal the wires, right? They have false ceilings, then they like to conceal the wires. Like, no, the entire wall is flush. You don't have this ugly looking plastic conduit sticking out nowhere, right? It's a thing. Some families have that. So they may, so that means the contractor will have to like, uh, drill or jack, right, a groove into the wall and then lay the wires into that groove, right, and then plaster it over, and then your wall looks completely smooth. You understand what I'm saying? So imagine, I mean, if you look at the wall right now, right, and I tell you that there's a wire behind inside that wall there. Okay, let's say there's a wire embedded in the wall. How would you know? Because I told you, right? So what happens if you buy over a house? Now this would be this. I'll tell you this. Okay, this might be a life lesson because that's what I'm trying to like do before I go for a short break. Right. This might be a life lesson. Let's say you buy over a house. Let's say you go to a house or maybe you stay in someone else's house next time. Okay. Right. Or when you're living abroad, sometimes there are concealed wires inside the wall. Right. And if let's say you want to go and nail and hang a picture, right? Imagine this, you go and nail the live wire is right there. Okay, right, boom, you fly off. Okay, not so bad, you basically just die on the floor. If you're living by yourself, that's it, right? Nobody will know. So so the idea here is sometimes there are concealed wires in the wall, right? So how do we know, how can we find out if there's a concealed wire behind the wall? So the good thing, the great thing is that in practical electricity, we learn that the wires, the current that's flowing inside these live wires, neutral wires, what kind of current is it? It's alternating current. So if let's say you have a wall, for example, right? So I'm just going to use this empty space here. Oh, that's an ugly looking wall. Hang on. Okay. Let's say you have a wall here, and then there's a cable, there's a live wire inside, right? The wall. Live wire is brown in color, right? So maybe I should go with brown. Right? There's a live wire inside there, right? It's embedded into the wall. You don't know where is it go, like where exactly it is, okay? And yet you're trying to hang a picture, you know? I mean, case in point, then just use the 3M stickers, Don't go and drill a hole into it, okay? But maybe you don't know, right? So the idea here is that the current inside the live wire will be alternating. So what you can use to figure out the exact direction, exact location of the wire will be a search coil. There's this thing called a search coil. Okay, so you could use a search coil. It's basically a coil of wire, right? It's called a search coil. It's called a search coil, and it's connected to a voltmeter. That's it. That's it. Because here's the thing. If you move this surge coil over this area here, what will happen to the voltmeter? There'll be induced EMF inside the coil. Why is there induced EMF? Why is there a change in flux? Because the current is alternating. So if the current is alternating, there's a continuous change in flux, there's an alternating change in flux, there will be an alternating induced EMF in the surge coil, and therefore the voltmeter will give you a reading. If you place it over a blank wall, of course there's zero reading, right? So it's only when you bring it over. So this is what electricians actually do, right? They have a nicer device, lah, right? Not this simple thing here like this, right? But there's that thing has a coil inside that uses it to search for wires embedded in the wall. So once it's here, if you bring it over here, the voltmeter will read a alternating voltage. Okay, right? Why? Because there's a AC, there's a continuously change in flux, so it's a AC. There's a alternating change in flux, right? There will be a alternating induced EMF. You get this? All right. If we're okay in this, let's take a quick one. Um, just pass some of the snacks around. Oh, is that it? That's pretty much it. Let me pass it around. Okay, yeah, take a quick break, guys. What y'all doing for youth day today? Let's go home. Parents are working, lah, right? Pass. Take and pass. Then if they don't want, then just put it back on where they are, where the empty space is. Yeah. Okay, I'm about to start soon, yeah. Yeah, it is. So depending on your teachers. So some teachers are like, you must always write magnetic flux linkage. Then yeah, just go ahead and write magnetic flux linkage. At the final exams, the O level exams, I'll tell you this, like there's never been a case whereby they said that you must write flux linkage, or if you write flux you get it wrong or anything like that. Like I look at all the TYSs, the sample exam keys and all that. Some schools have the word linkage, some schools don't have it, but it's just I think yeah, it's not the important thing is saying the change. Yeah, so that's the focus part. Yeah. Okay. So you see, right? The thing is this. So we go to level three now. Level three is where you realize that there is no area because now it's a single rod. Right now it's a single rod, and if you move this single rod in this field, it will also experience a change in flux. Okay, right? It's just that there's no area created by this rod per se. But I'm not saying that whatever I said was wrong. Okay? At the end of the day, once you move this rod across, the area that you're looking at, don't draw this in because it'll be very complicated if you draw this in. The area that we are looking at is the area that's been created by the rod as you pull it along. Then that will be considered the flux, right? The area that's been swept by the rod. Okay, so this rod itself, this is a single conducting rod. There's no area enclosed by it. But once you start moving, you can consider that the area that sweeps over as the area of the flux. Right? Remember, we started off last week, we said that what is flux? Flux is when magnetic field lines cut through an area, right? But if I use a single rod, where's the area? It's just one thin rod. There's no area, right? Okay, so in this case, right, in this case, a different perspective is that the area is created by the rod being swept over, right, being, brought over to the other side. Okay? Hmm. She's absolutely right. Sorry, yes. Before I erase that, I actually wanted to talk about that. Okay, so she's absolutely right. So when you start sweeping in, the area is like this much, and then when you start bringing it further, it'll be like this much, and you bring it further, it'll be this much, and you bring it further, it'll be this much, right? You can pull it at a constant rate, then the increase in the area is constant, right? Then the induced EMF will also be constant. You get what I'm saying, right? But here's the thing: I have never seen any school or any exam talk about the area. So you don't have to worry about the area. Don't have to try to like go and figure out what's the area or what's the size of the area here. Because I'm just trying to help you link to whatever I mentioned before. Because some of you may ask me, so where's the area now? Right? So I'm telling you that's what the area is. But for level three, this is a single rod being pulled across a magnetic field. Okay, single rod being pulled across a magnetic field. Right? Quite straightforward. You can just say there's a change in flux, there's an induced EMF. Is that induced current? So you could get, I mean, whatever it is, you realize that Faraday's law happens everywhere. Like, it's a kind of like number one, there's a change in flux, right? As you move the rod across. Okay, number two, there's an induced EMF. So is there an induced current? Anyone? Do you think there's an induced current? This is a single rod, a very thin rod. I just blew it up just for show only, right? I just drew it a bit bigger just for show. So the answer is no lah, don't have. No induced current. Right? No induced current. Why? Yeah, it can't flow. Correct. You're right. It can't flow. It's not a closed circuit. Okay? Right, hang on. Don't write can't flow because I'm gonna ask you to attach a circuit to it. So draw like some wires, right, attached to the two ends of this rod. So the idea here is this: as I pull this rod along, I got to ask you to imagine that these wires, right, are not pulled together with it. It's just kind of like these are very long, loose wires. So when you pull it across, right, there'll be induced current. You get what I'm saying? Right, there'll be induced current. So without the level one and level two type of understanding where's the north, where's the south, is it increase or decrease, right? Don't need. If it comes to a single rod, use your right hand rule. If it comes to a single rod, use your right hand rule. Okay, so my video, my kind of like in my video, my image is not mirrored, so I'm literally holding up my right hand. So we have to use the right hand rule here. Okay, but what are we trying to find? When you use your right hand rule, what is the purpose of it? Like, what are we trying to find? Direction of what? Of the current. Because that's the thing that's missing, right? I know that I'm pulling it this way to the right. So the force is pointing to the right. I know that there's a magnetic field pointing into the page. So the field is pointing into the page, right? And therefore, since it's a closed circuit, since it's closed, right? Now I closed it. I just kind of like looked over some wires and with a bulb there. There'll be an induced current sticking up like this, right? There'll be a induced current going upwards like this. So okay, go ahead, draw the induced current. So there will be, so as long as this rod is moving in the field, right, the induced current will flow this way. If you pull any faster, the bulb will become brighter. If you pull slower, the bulb will light up but dim. So no matter what, the bulb will light up. Huh? Oh, okay. So this is right hand rule, right? You realize that you see this picture, you can't place your left hand and make it the same. Like your left hand will not fit this picture. Like only your right hand will fit this picture. You know what I'm saying? So F is what? F is the force that you apply on the conductor, which is pointing towards the right side. So we can draw the F there. Right? I'm gonna apply the force here like this. This is F. B, I think I sort of like mentioned that B is the official symbol for magnetic fields. It's not in your Sec 4 syllabus, but some teachers are just funny, right? So sometimes they give you something like, oh, B field. Now, what are the three fields you learn? E field, G field, and then we have B field. So this is B field, magnetic field. Okay? So the magnetic field tells you where is it pointing. So for our case here, since they're all crosses, magnetic field is pointing into the page like this, right? And the force is pointing like that. And remember that it's the same thing as the left hand rule. Your three fingers, your two fingers and the thumb must always be locked in perpendicular to each other. You cannot like change, change the finger direction or something like that, right? No, it's just like that. Just lock it in like this and adjust your wrist until you hit the correct directions for everything. Okay, so current is flowing that way, right? So this is you using right hand rule, which is a shortcut. It's a shortcut. You don't have to do with the north and south pole. You don't have to go and deal with what increase or decrease in flux. It's just a very straightforward. I got a rod, I pull it across, right hand rule, induced current is there. Can? Okay, yeah, that's how it's done. Right. But what I want to point out to you is don't forget, don't mess up your right hand rule and left hand rule. Let me show you a way to remember the difference between right hand rule and left hand rule. Okay? All right. Let's spell left hand rule. Left. Let's spell right hand rule. Right. You see what I did there? I don't know whether it helps you. The left hand rule is meant to help you find the force. The right hand rule is going to help you find the induced current. Okay? Right? Literally. Like if you realize that, hey, there's no battery, I need to find the induced current. Right hand rule. Okay? Okay. One more question on this. There's an induced current, right? Is there an opposing force? Is there an opposing force? There must be lah. If you want to create this induced current, Lenz's law always says that there must be opposing force. Not that there will be, there must be an opposing force. If you have an induced current, there must be. If I didn't have the bulb, guys, if I remove this, oh shoot, I shouldn't have done that. I forgot. I can't undo, but okay, never mind. If I remove the bulb, is that induced current? No. Is that induced EMF? Yes. Okay, right? There won't be opposing force if you remove the bulb. But because you go and connect it, you go and close the circuit, right? You go and close the circuit like this. Let me just draw that again. Sorry, I should. Okay, the bulb lights up anyway. But because you go and connect it to a closed circuit, and then there's an induced current flowing this way using your right hand rule to figure it out, there must be an opposing force. Can anyone tell me what's the direction of opposing force? By guessing, how about just by guessing? Where's the direction of induced opposing force? Sorry, huh? To the left, lah, right? You see, some dude is trying to pull it to the right, correct? There's an induced current. What would the induced current try to do? Oppose this action, right? Oppose this thing, right? Oppose the change, right? So the opposing force will be pointing to the left. Let me show you another way, okay? Okay, let me show you another way. Listen, this is the part where both chapters combine. EMI, Now there's a current in a magnetic field. Use your left hand rule, go and find the force. You see, you created the current, right? You created current. This is your applied force. Now I'm going to ask you to use your left hand rule on this current, and you realize that the force is pointing backwards. You get this now? You apply this force. Okay, I'm gonna write this down. This is applied force. Okay, this is literally the force that you applied, like applied by me. It's like someone's pulling it. I pull it, I create the current. The current opposes my action. So sometimes I like to show students like this, right? You have these two hand rules, right? You put them side by side like that. You put them side by side like this. Okay? And then you see me face the board here like that. I apply the force to the right, the opposing force points to the left. Because the induced current is the current that's creating the force. You get what I'm saying now? So you have opposing force pointing to the left. Right? That will be opposing force. So you apply a force, then there'll be opposing force pointing to the left. Right? The current that you induce is going to work against you. But that's fine. That's how electricity is generated. If it was not the case, then you won't get electricity. Okay, now this is where EM and EMI combines. Right? This is us showing how the left hand rule and right hand rule are opposites of each other. Okay, good. Right. Another little detail about this. Right. This question is getting more popular these days because they like to ask it at IB and they like to ask it at JC level. Right. But then, in recent years, some of the secondary school teachers will be like, oh, wow, interesting question. Let me use that because they feel that, Sec 4 students can understand this. Right. So I'm gonna ask you this. Which end of this rod is a positive side? Which end of the rod is a positive side? I'm not asking you where's north, where's south, huh? I'm not asking you where the north and south is. I'm asking you which side of the rod is positive, right? So don't need to worry too much. Let me give you a simple way of understanding it. You just have to trace your current all the way, okay? You trace the current, you trace, goes into the bulb, trace, right? The current flows this way, right? Then I want you to draw another circuit on the side here, right? Can you draw another circuit on the side here like this, right? Circuit on the side like this. And basically, I want the current to flow in the same direction. So let's say I want the current to flow in the same direction, which is what, anti-clockwise. Like, how should I put a battery there in order for the current to flow the same way as this thing here? Like, how should I put a battery? I want to put a battery here so that the current will flow in the same way. Yeah lah, correct lah. The positive side on top, right? Yeah, good. Okay, your DC circuits are all intact as well. Right. So positive on top, negative below, right? And that's the same for the rod. So don't forget, right? Remember what I said last week. Induced EMF means that the rod is an induced battery. It's like the thing is an induced battery. So this time around, it's not a coil, it's a rod. So as I pull the rod across, this thing becomes an induced battery. So it has a plus and minus side, the plus side on top and the minus side below. Correct? This is how you tell. You can always tell by checking this. right? By drawing a side circuit, right? You're basically telling yourself that, hey, I know how the induced current flows outside. Okay, so I draw a current flowing outside here like this. How should the battery be arranged so that it will flow this way? Then the side of the battery, the side of the rod is positive, then this side of the rod is negative. Can anyone slightly like, oh, that means that current flows inside a battery from negative to positive. The idea of conventional current flowing from positive to negative is on the outside of the battery. One more time. You see this circuit here? Right? Current flows from positive to negative, right? But how about inside the battery? Inside the battery, how does current flow inside the battery? It flows from negative to positive. You see that? Okay? So, just kind of like, just take note of that, right? So, if I ask you, oh, where's positive, where's negative, you know what's going to happen? Most students will see this thing, induced current pointing this way, right? So they think that it must be plus at the bottom and minus on top because current must flow from plus to minus, right? He's right, you're right, but you forget that it's on the outside of the battery, on the outside circuit. So current will flow on the outside circuit from plus to minus. Therefore, for this rod here, it flows from plus to minus, right? So inside the rod, the current flows from minus to plus because this is the induced battery now. Can I? Okay, asking about where the plus and minus side is getting common, right? I see some in some of the prelim papers already. Okay, not? Can? Okay, if you're okay with this, then let's go back to the square loop again. Let's go back to the square loop again. This square loop, right? Now we can do things a bit faster already because I've already done all three levels. Level 1, level 2, level 3, right? I can do it faster now. Okay? Let's go back to this square loop again in a magnetic field. So if you have to draw it again, right? Because like the diagram was given to you, so you might want to just draw one for yourself now. So this loop is being pulled in, right? Is being pulled inwards into the field, right? Okay. The method that I used when I was teaching you this level 2, right? How did I teach you this? I was teaching you how about the increase in flux or the decrease in flux, right? Okay. Now we use shortcut. Shortcut. Okay, shortcut. You see this? This is a single loop of what this. I mean, this is the single wire, right? It's vertical, right? It's being pulled across this way, right? Use your right hand rule on it. Use your right hand rule on this vertical side. The horizontal side doesn't have any cutting of the flux, right? The vertical side just kind of like pass through like this, right? So you've got to use your right hand rule on this vertical side, right? So I'm pulling the wire this way. The magnetic field is pointing into the page, and therefore the induced current will be pointing up. And then that's it. That's a shortcut. Like if I ask you, like, oh, what's the direction of induced current in this loop of wire? The induced current will be flowing anti-clockwise because of my right hand rule. So why didn't I just teach this first, right? Then I don't have to go through the other version. Right? Remember that shortcuts are shortcuts for a reason because you already know what's going to happen. That's why they're called shortcuts. So this is a shortcut. But I want you to also take note of this. Where is the EMF induced? Where is it induced? It's induced on which side of this loop? It's on this side, right? Where does the induced current start from? It starts from this side. Then it starts to flow across the entire loop because it's a closed circuit. So then you can start drawing, oh, okay, the induced current flows like that. You understand what I'm saying now? How about when you're pulling it out? How about when the loop is going out? So you use your right hand rule on the back side, of this loop. Because the front side is already out already. He's out already, he's not experiencing anything anymore. So you use it here. Like that, like that. So you're pulling it this way, you're still pulling it this way, so the back vertical wire is still going towards the right side. Field is still pointing into the page, and therefore current is pointing up. So induced current is on the back wire now. Induced current is on the back wire now, right? Like this, and then the current will flow this way. And again, we use right hand rule. Okay, so now it goes this way, right? Makes sense now, right? I mean, just another way of seeing it. How about in the middle though? Can you use your right hand rule for when the loop is in the middle? I mean, you use your right hand rule on the front and on the back, right? On the front wire and on the back wire, right? Correct. Okay. So if you were to use your right hand rule on both sides, you'll realize that if there was an induced current on the front side, it will be pointing this way. If there was an induced current on the back side, it will be pointing that way. There's basically no overall induced EMF, no overall induced current, right? It cancels out, like what you say, the EMF cancels each other out, right? There's no change in flux, there's no induced EMF. Okay, so usually we don't even draw it, we just leave it blank. Our understanding is that there's just no change in flux, there's no induced EMF, there's no induced current. That's good enough, right? You use your right hand rule for shortcuts on the front and the back, right? So therefore, we can now go on. Yeah, we still got about a few more minutes left. Yeah, yeah, we are on good pace this week. We go on to the last thing. No, actually, second last thing. Sorry, last thing is transformers. Yeah. No, wait, hang on. O level syllabus, like no more transformers already. Wait, let me see first. Let me double check first. You're there already? Oh, okay. No, it's only the that means it's only the IB that was taken away. Let me just double check first. Yeah, transformers still there. Okay, transformers. Okay, okay, it's still there. So we are basically, yeah, yeah, AC generator. Yeah, okay. Now we're gonna go there now. Okay, so this is the AC generator. After all of that, after everything's been said and done, okay, we come back to this diagram, right? Of course, obviously this page says AC generator. You can see that the header of this page says AC generator. Okay, AC generator. It looks a lot like it looks a lot like the DC motor. Like you almost might not even realize that there's like some differences. Like what are the key differences between this and the DC motor picture? Okay, so what has a split ring? DC motor has a split ring. This thing is called a slip ring, right? This thing is called a slip ring. Okay, these are called slip rings. What's another key difference? What one very important difference? What does a DC motor have that the AC generator does not have? Battery. There's no battery here, right? It's the same thing as this thing here, right? There's no battery inside. I mean, there's a small little capacitor inside, but there's no battery inside. If I stop spinning, it doesn't light up. If I spin, then it lights up, right? So there's no battery here. So what we're trying to do is we're trying to generate electricity. Okay. So in order for us to learn this, right, you just basically have to turn that coil around, right? You have to turn the coil around. So I'm going to use this as a representation of this coil, right? So imagine the edges are the coil, right? So the coil like this, right? And we're gonna turn it. So as we turn it, there'll be induced current, right? Because the whole circuit is now a complete circuit, right? There'll be induced EMF, there'll be induced current. So when it comes to AC generator, you simply just use your right hand rule. Don't need to talk about north pole, south pole. Don't need to talk about increased flux, decreased flux. Just simply use your right hand rule, but you got to use it correctly. Number one, where's the flux? Where's the field lines pointing? The field lines pointing from north to south. It's pointing towards the right. Okay. This picture, like just to help you understand, what we're gonna do is like this thing is to be rotated. So one side is gonna experience a force out of the page, another side is gonna experience a force into the page. Right? So it will rotate like this. You understand that? Right, it will rotate like that. Okay. So this is what we call the top view, right? I think we mentioned this in DC motors as well. This is the top view. So you're looking at it from the top. All right. So once this coil on this side is experiencing a force out of the page, right? And the field is pointing to the right. What's the direction of induced current on this side? Yeah, use your right hand rule. That's it. Use your right hand rule, right? Tell me what's the direction of induced current in this wire. It's either going up or it's going down. Up, huh? Everyone? Is that right? Okay, let me try this out. So force is pointing out of the page. So I'm gonna draw a dot. I'm gonna label F. Right? So there's a force applied outwards. Field is pointing to the right, right? So my first finger must point towards the right. So the force must be sticking out of the page, right? Like this. And then when I raise the middle finger here like this, right, then current is flowing upwards like this. Okay, so the induced current is definitely going from here to here. So that's the induced current. Okay, I might have to ask you to start labeling this one as well. This is like A, B, C, and D, right? I know you know that the current is going to flow over here and it's going to flow down anyway, but just for the sake of using a right hand rule, right, practice using it, right? So the force is going into the page, right? Because this side is being pushed in, right? One side is being pushed out, one side is being pushed in. Field is pointing to the right, and therefore when you stick the middle finger out, right, it's pointing downwards. Okay, it's pointing downwards like this. So the induced current will be pointing downwards like that. Okay, this is the next most important part. Using your right hand rule is considered basic standard already, right? Yes, I know I said level 1, 2, and 3, right? But these are the basic requirements, right, of what you need to know when you're doing the questions, right? When you start applying to the questions. So what I need you to do, second part that's really important, is to trace the current through the entire thing, right? This is where a lot of students, they don't bother doing, right? They don't trace the current and then therefore they're like, I don't know how this works. I don't know why I got it wrong. So if you trace the current, right, I'm going to trace. Notice how one of the wires slips through one of the rings, right? Guess why it's called slip rings now. So this wire is not touching the this ring. This wire is actually slipping through the middle. So the current goes to this one. It's connected to the ring. It's connected to the carbon brush. Current will flow this way, right? And then you complete the trace, right? So the current flows, right, like that, all the way. Okay. So when we rotate this coil, as we rotate the coil will flip over like this, 180 degrees, right? So not 360 yet, so half a turn, right? So it's basically from here, right? And I'm rotating it this way, half a turn, right? So this is the second picture. So where's the A, B, C, D now? The A will be here, the B will be here, the C will be here, the D will be here. Okay, right? And when we rotate something, we try to always go with a continuous rotation. It kind of like doesn't really make sense if you're trying to do it like that. It's not a very smooth motion, right? So you want to just keep on rotating the same way, right? So which means that if this side was pointing out at first and this side is pointing in like that, right? The force, and as it flips over, then this side will experience a force out and this side will be facing in, which means that this side will experience a force outwards and this side will experience a force inwards. We use our right hand rule again, right hand rule, figure out the direction of currents on the two sides here again, and you realize, oh, it looks like the same, right? Induced currents pointing up on the left side, induced currents pointing down on the right side. You see that? But it's different because the current was previously flowing from A to B to C to D. Now on the flip side, 180 degrees later, right, the current is now flowing from D to C to B to A. So the current has changed direction. You might be thinking, hey, doesn't the split ring DC motor does that too? Doesn't the direction change as well? Yes, it does, but it's still called DC motor. This is the AC generator, right? So get it in your head. You can't mix up. There are such things as AC motors, there are such things as AC DC generators, but that's none of your business. Your business is DC motor, AC generator. Okay? And then you trace the current though. So let's trace the current. And notice this. This is the part where you might get a mistake. So this wire here is connected. Look at how there's an L joint here to this ring. So the current will flow over to this side. It'll flow to that side here like this. Okay? Right. So it flow through the bulb, flow through the bulb, flow into the ring of the other side, and then flow and slip through the ring again. Right? Slip through the ring like this. Okay, so what do you notice about the bulb then? What does the bulb get? As you continue rotating and rotating and rotating, yeah, left to right. I'm sorry, right to left to right, right. As you keep on rotating, right, you go back again, right to left to right to left to right. This is alternating current, right? You're basically generating alternating current now. Okay, so your voltage or your current, right, will be alternating like that. Okay, if one side is positive, then the other side is negative, right? So if this direction is positive, then the other direction is negative. Cannot. So this is for a power generator. Now in the actual power generator factory thing, right? Power plant, right? In real life, okay? The setup, the simple schematic of it sort of looks like this, right? But how do we get this thing to turn? How do we get the coil to turn? So it's not a whole bunch of laborers there turning the coil at the same time, right? That's not how electricity is created, okay? Right? That's the olden times, right? So it's never happened before, right? So how do we get these coils to turn at a power plant? Let's talk about power plant, huh? Steam. Where's the steam gonna come from, man? So you need to burn something to boil the water to create the steam. Then the steam will cause these blades, right? So there's blades attached to these like there's turning blades attached to this coil here like this. Let me just try to draw that. Okay, okay. You heard of the word turbine? That's a turbine. So an AC generator is a turbine. So like what you say, right? You burn something, you boil water, you get steam. Steam will be used to push the turbine. The turbine will turn, and that's how you generate electricity for the whole of Singapore or anywhere else in the world. Nuclear power plants, what do? They do nuclear fission. They create heat. Heat boil water. Water becomes steam. Steam turn turbine. Same thing. Hydroelectric dams. How do they work? You have a reservoir of water. You release the water coming out from the bottom. The water flow. The water turn the turbine. Electricity is generated. Wind turbines. Wind blow, turbine turn. Okay, that one don't need much connection there. Okay, solar panels. Solar panels completely different. Okay, solar panels is a completely different thing. In fact, solar panels generate DC. Okay, so you know that Singapore has this huge solar farm, right? At this place called the Tengeh Reservoir, right? Somewhere in the Kranji area, right? It creates DC. In fact, for that farm, they have to convert it, they have to invert it into AC, right? They invert it into AC for our use because we supply electricity to all the households in Singapore as AC. Cannot? Okay, so there you go. This is how power is generated. Right, let's just finish this up. Let me see. Is there any other things here? Okay, I'll tell you what. I don't go to the next page. Let's just stick here first. How will you increase the voltage that's being generated? Spin faster. Any other methods? So if I want to increase the voltage, I want higher voltage. What can I do? You say spin faster. That's correct. So higher V, you spin faster. What else? Stronger magnets. Good. That's another way. Stronger magnets. Okay. Any other ways? Any other things? Stronger magnet. More coils. So if you have more coils, you have more turns, you can generate more electricity. So more turns of coil. Anyone with a last method of increasing the V? No. Wider might be weaker. I mean, technically speaking, you can bring it closer, but we usually don't use that as a suggestion, because if you bring it closer, then the coil will become smaller. Then if it becomes smaller, then the area is smaller. Then that kind of like, so the engineers must find a good in between, right? That's their business, right? All we need to do is just to know like what the like these four lah, right? So there's one that you've learned before. It's something that you learned before in magnetism. In magnetism, that's the correct answer. So you can put a soft iron core in the middle, like this, right? You can put a iron core, right? And the iron core will do what? What would it do? Concentrate the magnetic field lines, and therefore the induced voltage will be higher, right? So yeah, if you have a combination of all of them, then it's even better. Okay, right. I'll continue this next week. Next lesson, I'll be able to finish this. There was an instruction to finish one paper. Was there? Nanhua paper, right? Which is the one that's uploaded. I mentioned that it's due 14th of July. Just paper one. Just the first paper one. And the point of making you, what's wrong, my throat? And the point of me making you do this, it's called end of year 2025 prep. It's so that, sorry, it's so that we can figure out what you're still not sure of, what you're still weak at. Because I don't know what you don't know, right? But if you tell me at July, right, of 2025, you still don't know everything, then I'll just say that it's impossible for me to go through everything from scratch, right? So we need to kind of like find the targeted topics for me to cover. It might not be the entire topic. Some of you thinking like, oh, I don't know how to do this question, so my work energy power, the whole thing is gone. No, it might be just a small mistake that you make. So I don't know. I also don't know. Right? So do the paper, right? Then we discover what you're not good at. Okay, thanks guys. Bye bye. Bye Ben.